Hi. Okay, so today we're going to go over the comparison test. Okay, there are two of them. Okay, here and here. So before I go over what they are, although looking at them, you may have heard of these from older lessons. Before I go over them, I just want to go over some of the other tests. So far, we went through the first test for a geometric series, whether it converges or diverges. And if it converges, this is the one scenario we can find the sum, what it converges to. Okay. For our second test, that was the n-term test. I'm going to come back to that. Okay. Our third test, this is the integral test. Okay, and so hopefully you can determine whether it converges or diverges. Okay, the fourth test, a p-series, we use that to find if it converges or diverges. Okay, so far all the tests can tell us if it or if our infinite series converges or diverges, except for that second one. Okay, that second one, the n-term test. Okay, is just for divergence. Okay, so we know if it diverges or if it's inconclusive. I'm just jotting that down. So you may want to go on to proceed to see if it does converge. Okay, especially if it's inconclusive by one of these tests. Okay, so that actually leads that this is like our fifth and sixth test. Now, there's a lot to this, okay? If you want to pause the video, stop it, and jot these down, you're more than, please do, okay? I'm going to suggest that, yeah, go do that if that's your thing. It's very wordy, very long, and I feel that just explaining it in clear words is a lot better than jotting this all down. You can take a picture of it from any textbook, any workbook. Actually, the notation may be a little bit different, but how you understand it is going to be the same thing. Okay, so let me get to the understanding while I erase some of this ink. Okay, so in a direct comparison test, okay, you're going to have a sub n eventually be a function. Okay, so what they give you, and then you have to compare it to a different a sub n. That's going to be a little bit tricky to figure out, well, hey, what should I use? Okay, because it's really your choice. Now, once you know the function you want to compare it with, maybe the one you want to compare it with is above, okay, or below. I'm giving like two scenarios. So this is the bigger function because the y values, okay, are throughout bigger than this one. And this one's smaller, okay, because, you know, it's small, its y values are all smaller than this one. All right, so these are the two scenarios. Oops, let me erase that. Okay, so let's talk about convergence and divergence and use the geometric or the infinite geometric series as an example. So in an infinite geometric series, when it diverges, the values keep getting, or this is a possibility, it could be arbitrarily large and positive or negative. So let's say if it diverges, okay, what happens is as you keep finding the sum, it keeps going towards infinity. And converges, okay, it goes towards a particular value. Now, let's say that value is 0. Okay, in our lesson for the n-term test, we did a limit where it equals 0, and we kind of used that contrapositive to understand the n-term test. So these are like the best kind of understanding. So if let's say you're given an a sub n here, that's your original, okay? And you figure out some other a sub n that you can use to compare it with. Well, here's the scenarios, okay? So for the example where the smaller one of the two, let's say that continues to get bigger and bigger. Well, this right here has to also go up because then it just kind of intersects. And that's not going to be true. It would suddenly not become bigger anymore. It would become smaller. So if it's consistently bigger, it too has to also go up. Okay, so if out of these summations, okay, you figure out, well, this is the smaller one and this one diverges, then we know the other one also diverges. Okay, so let's talk about convergence. Okay, so it's getting towards 0. Well, if this top one gets towards 0, that forces this bottom one to become 0 as well. Again, it couldn't start going up because then one wouldn't be bigger than the other. So if you have a bigger function that you know converges, then the smaller function, it too converges. It also converges. Okay, and that's what's going on in the direct comparison test. So let me explain the limit comparison test. Okay. Well, in the limit comparison test, you may be looking at these fractions. Okay. So basically, if you have two different like a sub n's, and here they're saying like b sub n. Okay, it doesn't matter which one is in the numerator or denominator, so you actually don't need to know which one is bigger or smaller, and that makes LCT easier to do than DCT. If you take the limit of them and it equals some number, okay, that number has to be finite and positive. Okay, so that's important. So it can't be infinity. That would not be good. Okay, and it has to be positive. Okay, I know this says like 0 here, so it can't be 0 or negative. All right. So what this kind of tells us is that if you get an answer that is finite and positive, okay, so let's say it equals 2 or it equals 1, some sort of answer that we want, then we know that the series both converge or both diverge, okay, and that's your limit comparison test. Now, we kind of said before about the limit equaling 0, about its convergence. Okay, I mentioned on the previous slide. You could go back to the other tests. And infinity, how it's, inconclusive on other tests. So you can kind of continue that over here. But basically, the limit comparison test is this big deal right here. And I'm scribbling over all of it. So let me just show you some examples, and I'm sure it'll make sense. First, we're going to do DCT, and then we're going to do LCT. Okay, so these are the ones that we're going to do the direct comparison test for, and the next two we'll do the limit one. Okay, so for the direct comparison test examples, okay, so we're going to take a look at a function like this. We have n over n squared minus 3. So the first thing that we want to do, okay, make sure that you get a chance to copy this down. Okay, summation of n over n squared minus 3 from n equals 2, that's okay, to infinity, still an infinite series. Okay, we want to first find something to compare it with. So forget the minus 3 for a second. That's not going to make much difference. We'd maybe work with something like this. Or perhaps, okay, we have to continue to break it down. So we're actually looking at this series to compare it with, okay? So that's a good comparison with the original. Okay, we know 1 over n, and 1 over n, for n is greater than or equal to 2, what's going to happen to its values. So now if you look at the original, okay, this one's going to be larger because you may have the n squared in the denominator. So you may be thinking, okay, that's going to make the denominator larger, which means that all the answers will be smaller than 1 over n. However, because n is also in the numerator, okay, you can even think of this as like you divide everything by n. So it's 1 over n minus 3 over n. So now if, let's say, n is equal to 2, here we would get 1/2, okay? This would be 2 minus 1.5, so it's a half. And the answer here would be 2. So this one is much bigger than this one. So this is the bigger function if we make it an f of x, and this is a smaller function. All right, so now that that's understood, okay, so now if you take a look at 1 over n, okay, 1 over n is not a geometric series where you can kind of like look at the graph and determine what's going on with the values, but it is a series that we went over. Okay, this is a harmonic series. Okay, we have 1 over n where p is equal to 1. And if p is equal to 1, then the series diverges. Okay, 0. I don't need the 0 is less than, p is less than or equal to 1. Okay, so we went over that. And if this smaller one, okay, is diverging, so I'm going to go back to that diagram even though it's not for this particular series, but if that smaller one is diverging, it's going to force this larger one to also diverge, okay? So since, okay, this diverges and 1 over n is less than n over n squared minus 3, then I'm running out of space. I'm going to need this space up here. Okay, then the original also diverges. Okay, let me just finish the sum here. And that is the first one. So let's take a look at the second one. It's pretty complex, but don't worry too much about it. Okay, so if let's say, and I kind of wrote this one, this was our function. Let's talk about the numerator. So the numerator seems complex. It's a trig function, but it's sine of x times sine of x. It's something that's squared. So even if you used every value, okay, for x, since you're squaring, it's going to be positive. So this is entirely above the x-axis. And all our values for sine, like our answers are between -1 and 1. Well, now it's between 0 and 1. So for any value of x, if it's between 0 and 1, let's ask, not that it's going to equal 0, because that's going to be hard to compare it to. Let's say it's 1, okay? So now if we're working with the denominator, and I rewrote it this way, kind of like what we would do with n behavior model, take like the square root of each one. Okay, now if you're looking at it this way, you don't really need the +1 to understand like how we should kind of go about this particular series. So let's compare it with this series, and I hate that the arrow is there. There we go. Much better. So let's compare this series with this one. So now let's also figure out which is the bigger one and which is the smaller one. So we can see if we can use the direct comparison test. So if we were to like plug in values, this one's going to be bigger than this one because we got like that square root in the denominator. So that's going to make, I'm sorry, we do have a square root in our denominator. This one's going to end up being the smaller one. If you're not sure, like I said, you could plug in values. I have no direction as to whether it's a calculator problem or not. I have a funny feeling that it would be, considering that you do have that trig function in there. But in any case, I went through how we don't need the trig functions, just trying to evaluate some answers. So maybe if you had n be 0 for the original, then you have 0 over 1 as an answer, and that wouldn't work for the next one. But if, let's say, you work with pi over 2. Okay, you're going to cube that and take the square root of that in the denominator here, and pi over 2 for sine is 1. Okay, so it's going to end up being very similar of an answer since, let me take the red, since that's going to have the same answer as this, but you're adding 1. Okay, so it makes it smaller because there's a bigger value in your denominator. And if pi over 2 doesn't work to make sense for you, you can pick other angle measures to see if that works as well. But the denominator would be bigger, making this expression the smaller one, and this one the larger one. So now let's take a look at whether we can determine if this series converges or diverges. All right, so this is not a geometric series, but it is a p-series. P would be equal to 3/2. And because P is equal to 3/2, and 3/2, okay, is, I don't know what I'm writing, is bigger than 1. Then this series converges. All right, therefore, okay, so remember this was the smaller one. I'm just going to move that over. And this is the larger one. So if this larger one converges, that forces the smaller one to also converge. Yay. Sometimes you're not going to make a conclusion. Let's say your smaller one converges, then you know nothing about the larger one. and let's say your larger one diverges, then you know nothing about the smaller one. So it's got to actually fit into the direct comparison test. Okay, I'm just proving this series also converges. I should have written out the original function, but this was a lot to write out in the first place, so I think that should be good. So let's take a look at the limit comparison test. Okay, so the limit comparison test is going to be a little bit easier because it doesn't necessarily need to have a bigger one or a smaller one. You just got to get used to trying to figure out what that other series could be. Okay, so we're going to do the LCT here, the limit comparison test for both A and B. So same directions, different sums. Let's take a look at each one of them. All right, so in A, we have the summation of 1 over the square root of n squared plus 4. Okay, so we can say 1 over n plus 2 as our sum, but that should be really just 1 over n. This is a good comparison one for this. Okay. Doesn't matter if we add 2, it's going to have the same behavior. Okay. And like I said, it doesn't matter which one's the bigger or smaller now. We're going to take the limit, so it's more mathematical. And it doesn't matter which one is in the numerator, because you need to take one and put it in the numerator, and which is in the denominator. Okay? So typically, the original one is in the numerator, but like I said, it really doesn't matter. And we're going to take the limit of this expression as n approaches infinity. Okay? So, in this particular case, we have a complex fraction, and we simplify our complex fraction. And we can take the limit. Now, if you want, you can do L'Hopital's rule. Again, we can continue to look at n behavior model. So this is the same thing as like the limit of n over n plus 2 as n approaches infinity, limit of 1 as n approaches infinity, because it's just going to be n over n, and so the answer here is 1. So this is a finite answer, and it is greater than 0, which is what we want. So therefore, we can conclude that the original, okay, and this one okay, I'm trying to write it out. So hard to write on the iPad. Okay, and this one. Both, now we have to determine if they both converge or diverge. Well, we should know this one because we've seen it before. Okay, we already discussed this. The summation of 1 over n is your harmonic series, and it diverges. Okay, so that means that both of these diverge. So now, let's take a look at part B. Okay, so this is the second one we're going to do with a limit comparison test. Okay, so let's find something that we can use here. Say 2 over n, 2 to the nth power over 3 to the nth power. Okay. Well, this is a good one to use, believe it or not, because, and I'm not going to actually use this when we take the limit, but we can rewrite this as 2/3 to the nth power. Doesn't matter if this is n equals 3 or 1 or 0. If you have a number raised to some power of n or x or whatever index is there for your sum, this is a geometric series. We have an infinite geometric series. So we should be able to tell if it's divergent or convergent. If it converges even, we know it's sum. So let's take a look at our comparisons. So now, let's compare these two. We're going to do that by doing the limit of the numerator over the denominator. Okay, so this is still the numerator. Like I said, typically it's the first expression, the original one, and the second one being in the denominator. Okay, and this is as n approaches infinity. This is going to be our limit. So let's do keep, change, flip here. Whatever you use to simplify your fraction. So you get actually 3 to the nth power over 3 to the nth power plus 1. And again, you can use n behavior model or L'Hopital's rule. You just have to write out the actual expression correctly. So this is the same as taking the limit of 1. Now, it just so happens these two end up having an answer of 1. Okay? And again, if you get a number that is positive, not infinite, then we know that either both series converge or both series diverge. Okay, so yay, we can make a conclusion. Okay, so both series in part B, okay, and I'll label it with sum sub 1 and sum sub 2. That's supposed to be the 1. So I don't have to write that whole thing again. Let's see. Now, what do they both do? So if r is equal to 2/3, that means it's between -1 and 1, so the series converge. So they both converge. Both series in B, which is S sub 1 and S sub 2, converge. Okay, now we would know what this sum is, but that doesn't mean that we know what this sum is. So all we can conclude is that both of these converge. So whenever you do this, you're either knowing that they both converge or they both diverge for LCT. All right, so hopefully you got that all down. Well, I just summed that up for you. Don't forget you also did DCT here, and those are your 2 comparison tests. Good luck.